we were talking about the basic of the heat transfer, basic concepts of the heat transfer, and we were just discussing this example. Okay, and the purpose of this example is to show you how you can draw the free body diagrams related to these kind of thermal systems, and how you can represent different type of energy interactions with the surroundings. Okay, now you can see the statement. I would just read it down. The blades of a wind turbine turn a large shaft at a relatively low speed. You can see that these are the blades. These two are the blades. Okay, this is basically the side view of a wind turbine. The rotational speed is increased by a gearbox that has an efficiency of eta GB is equal to 0.93. It means this rotational speed, obviously the wind basically drives these blades, and as a result this shaft starts rotating, this shaft. Okay, now you want to run the generator through these blades. Now this is the gearbox by which you can increase the RPM. Okay, efficiency of the gearbox is given, this is 0.93. In turn, the gearbox output drives an electrical generator with an efficiency of 0.95. Right, the cylindrical nacelle, you can call it nacelle as well, this is generally known as nacelle, which houses the gearbox, generator and associated equipment. This is the cylindrical nacelle, right, where you can see a man standing there. Okay, this one. This is the cylindrical nacelle, right, and associated equipment is of length L equals 6 meter and diameter equals 3 meter. If the turbine produces 2.5 megawatt of electrical power and the air and surrounding temperatures are T infinity equals 25 degrees centigrade and T surrounding is 20 degrees centigrade respectively, determine the minimum possible operating temperature inside the nacelle. Okay, obviously the temperature inside the nacelle would be different from that at the outside. Okay, that's how you can have some kind of energy interaction, some kind of heat flow from the system to the surrounding. Okay, the emissivity of the nacelle is 0.83 and the convective heat transfer coefficient H equals 35 watt per meter square per Kelvin. The surface of the nacelle that is adjacent to the blade hub can be considered to be adiabatic and solar irradiation may be neglected. Now this surface can be considered as adiabatic. Now what do you mean by adiabatic? Sorry? No heat interaction or no energy interaction is possible through this surface, right? So what is the purpose of showing this surface as adiabatic? That there is, these three sides should be used to calculate the surface area, isn't it? For this problem, these three sides should be calculated as the surface area to find out the total heat transfer from the surface or to the surface. Now the point is, you need to find out minimum temperature inside the nacelle. Okay, and there is some information given about emissivity and the H coefficient. Now if you see, energy can go out of, if I consider this nacelle as the system, I consider this nacelle as the system, I would isolate this system from its surroundings. This is my system. Now how many kinds of energy interactions are possible? Through convection and through radiation, right? And what would be the associated area, surface area for these two kinds of energy interactions? This cylindrical side and this, right, these two sides are kind of cylindrical these circular sides. Now this side is adiabatic. So you need to know this surface area, the cylindrical surface area, and this area. So what is the cylindrical surface area? It can be taken as 2 pi RL plus pi r square. You know what is r? This is the radius. R is the radius. The diameter was given, and this is L. You understand that? Right? So these kind of energy interactions are possible. But alongside, look at the statement. It is given that the turbine produces 2.5 megawatt of electrical power. Right? So it means some energy is being converted, let's say, from mechanical to electrical, isn't it? Because the shaft is being driven by the wind, and if the shaft is being driven by the wind, it is basically the generator is trying to convert that mechanical energy into the electrical energy, right? So you can say that there is some kind of energy generation within the body. That's how you see the energy generation by heaters as well, isn't it? So your heater does what? Electrical to heat, right? Similarly, the turbine is doing what? The generator. It is converting mechanical to electrical energy, right? And similarly, some kind of work is also being done by the blades, right? So because the blades are doing some work on the turbine, and that is why that kind of energy is being converted into electrical energy, right? Now my point is, if you look at the total energy for this system, there is work which is being done on the system by the blades. This should be plus, because this work is being done on the system, and then energy is being generated by the system, isn't it? Energy is being generated by the system, okay, fine. And then what? This energy is also being sent outside through conduction and convection and radiation, okay, and this is going to be 0. Now do you understand my point? Oh, we will talk about that, just hold on. We would see how we can classify those two kinds of radiation, but this is how you can apply law of conservation of energy on the system. Sorry? If you look at this term, EG term, this is essentially not the generation term, but it is the output of the system, isn't it? This is something which the generator sends out of the system as its output, right? So essentially there should not be a positive sign, this is a negative sign. Why? Because this energy is being generated from this power, okay. Now this is the point. So this is, sorry, you are talking about this negative sign. So my point is, this energy is being generated, fine, but how this energy is being generated? Out of this work, right? So what is the actual input to the system? This is the total work which is being done by the blades. Now this work is being converted into some form of output, which is the energy generation, because that electrical energy is a part of this work, isn't it? And the rest of the energy is sent outside of the system by radiation and convection. Do you understand that? Right? So essentially this is not a generation term. Essentially it is the output term. Okay. So just because of these points I chose this example to discuss in this class. So my point is, how can you know what is this output power that was given? That was what? 2.5 megawatt, isn't it? So that was 2.5 into 10 raised to power 6 watt. And you know what is this Q? I am sorry, this is, you do not know anything about Q. You can only know about what? Oh, I'm sorry, this should be So what is that Q? It is a combination of two, Newton's law of cooling and Stephen-Boltzmann law. Newton's law of cooling and Stephen-Boltzmann law. Now, how you can calculate this W? If you know the output, let's say if you know the output, now I am talking about this output. If you know the output, how much is this one? 2.5 megawatt. Now you know the efficiency of this system and you know the efficiency of this system. What is coming in? Obviously, if I represent this as P, this would have been multiplied by this, and then it would have been equal to this thing, isn't it? That's how you convert. Let's say if a system efficiency is eta and you are putting this much kind of energy, let's say P, so what would be the output? Eta multiplied by P, right? That's how you find out the output. Now my point is, you can find out this W by considering what? Eta of the gearbox, eta of the generator, multiply by not multiply by, I think this I'm sorry, yes, this should be divided by this 2.5 into 10 raised power 6. Why? Because this P or this W should be multiplied by eta G and eta gearbox to find out this energy generation or energy output. This is 0.93 and this is 0.95. You can find out the energy generation. This EG is what? Obviously that is being produced by the rotation of the turbine. So you can say why I am using, although it is the output of the system, it is the output of the system, right? But my point is, because this is being generated within the system, so that is why I am using this notation. Being generated within the system, why? Because you convert the mechanical energy to the electrical energy, right? So this is the equation. Now can you find out this Q? You can find out Q in, let's say, in watts, for example. Now this is law of conservation of energy. Now no, W divided by this equation. Yes. No, by the way, where is this energy going on? Why is this efficiency not equal to 100%? So obviously that energy has been lost to the surroundings. Why do you say efficiency can't be equal to 1? So that is how a heat is being produced, and that is how it is being sent out of the system. Okay, when you multiply it with 0.93 and 0.95, obviously the rest of the heat is going out of the system, because the energy cannot be stored in that system. If you start storing the energy in the nacelle of a wind turbine, or let's say in the generator or in the gearbox, it would burn, right? So everything needs to go outside. Either it is the output of the wind turbine or it is something which is going out. So because we are talking about the steady state conditions, we are not involving any kind of time over there. I hope your question is also answered. Okay. So this Q is basically what? This Q is a combination of Q convection plus Q radiation. Now do you remember we found out something as HA Ts minus T infinity for Q convection, and then we have HR Ts minus T surface for Q radiation. You remember that? Right? And what was that HR? This H for radiation was equal to epsilon sigma Ts square plus T surrounding square Ts plus T surrounding. Now you know T surrounding, you know Ts, you don't know by the way Ts. That is what you need to find out, isn't it? What is the requirement of the system? determine the minimum operating temperature inside the nacelle, right? So that is something which is T, which is representing Ts. Okay, so just plug these values back into this equation. You know this amount of Q, you know everything else. Now what is the associated area? Obviously you also need to multiply this with area as well. Why? Because it is also being used for sending out the energy. So use this relation, use these two relations to find out Ts. Okay, that's the point. You can see the solution in your book. My point was just to show you. Now you know H, you know A, you know T surrounding and infinity. What is unknown? Ts. So it would be kind of an algebraic equation for Ts. You might be getting more than 2 values of Ts, right? If it is a second order algebraic equation, you would be getting 2 values of Ts. Yes, then you should have incorporated this area as well. Okay, the only point in this discussion is that you should understand how you can apply law of conservation of energy, just like you did law of conservation of kind of forces on the dynamical system or on the static system, and you do the same thing with the heat transfer thermal systems as well, right? So you should understand how to draw the free body diagram, and you just need to look what kind of work is being done on the system, what kind of energy is being sent out of the system, and how it is having convective or radiative heat transfer out of its surfaces. That's what you need to do. Okay, so this is just one example for these kind of systems. So okay, now I would move on to the discussion on conduction. Right, now we are going to discuss conduction in detail, and related to conduction, we would discuss it in the following order. First of all, I would talk about steady heat transfer. What do you mean by steady heat transfer? That in the governing equation you have partial by partial T equals 0. Okay, there is no change with respect to time, and we are talking about change in the temperature, right? So you would see that we would derive an equation which is known as heat diffusion equation, and that equation would carry a term partial T by partial T, variation of temperature with respect to time, and we would consider that as a 0 term, right? We would not consider the temporal effects or the unsteady effects initially, and then we would incorporate those unsteady effects, and then we would talk about the geometrical simplicity of the system. Initially we would only consider 1D system. Now what do you mean by 1D system? That you are considering heat flowing in only one direction. And what do you mean? Let's say if I ask you that there are 2 temperatures on the 2 sides of the wall. So for example, if that wall is of an infinite height, it means those ends cannot be seen by the temperature. Let's say by the temperature difference or the heat, that cannot be felt, those 2 temperatures on the sides, top and the bottom. Why? Because wall is having an height of infinity. So obviously the heat would have no choice other than going in the straight direction. Okay, so that's how we can theoretically model these 1D systems. Okay, and then we would add dimensionality into it. We would talk about the 2-dimensional systems, how heat can travel in one area, let's say on a plane wall or on a cylinder surface. Those can be considered as the areas 2D. And then you can talk about 3-dimensional heat transfer. Generally for 3-dimensional heat transfer, we might be more interested in the numerical technique, how we can find out the numerical simulations, numerical results. Okay, because it is very hard to find out the analytical results for these kind of systems. Till 2-dimensional it's fine, we can do it, but beyond that obviously you need numerical. Okay, and we would try to use some kind of MATLAB codes, or we can also use Fluent as well. I would try to give you some assignments so that you can have an idea. And we can also discuss those things with other coordinate systems, spherical and cylindrical, right? I would do the derivations in the class with rectangular coordinate systems, and I would just show you the final equations for the other coordinate systems. And from your calculus course, you already know how you can switch from one coordinate system to the other one. Okay, you might be remembering those kind of transformations, x equals r sine of theta if you want to go into the spherical or the cylindrical system, or r cos of theta. Okay, and finally at the end of this topic we would discuss the boundary conditions, right? So you can say that this chapter which we have started from Incropera's book, we would discuss this topic and this topic in detail. I would derive the heat diffusion equation and I would talk about the boundary conditions. Okay, now you know these are the coordinate systems, and these coordinate systems are chosen based upon the geometry of the system. Let's say if you have a plane wall, obviously you would go towards Cartesian coordinate system as the choice, as the reference frame. Okay, if you are having a pipe flow, you already know that you would choose a cylindrical coordinate system. Okay, and if you are looking at, for example, some spherical object, any spherical object, you want to look at the fluid mechanics or the heat transfer around a sphere or within a sphere, obviously you would choose the spherical coordinate system, right? So these are basic three coordinate systems which generally we use in engineering modeling. Now this is how you define steady and transient heat transfer. This is just a formal definition. The term steady implies no change with time at any time within the medium. At any time, if you see that one side of the wall is at temperature T1 and the other side is at temperature T2, there would be no change at all with respect to time. T1 would remain T1, T2 would remain T2. Okay, and the term transient implies variation with time or time dependence. It means, let's say if you see that temperature would be a function of what? X, Y, Z and T. For example, it has some spatial dependence and the temporal dependence. Now if temperature becomes a function of X, Y and Z only, there is no dependence on time, it means this is a steady state phenomena. Okay. Now obviously we are not considering any kind of time. It means that heat transfer rate needs to be constant. You remember that in the very first class I told you that I am talking about the steady state term with respect to what? A constant rate of heat transfer. And that constant rate of heat transfer is only maintained when the both sides remain at the constant temperature. Okay, if obviously the temperature would vary, right? But to keep the systems very simple, at the initial stages, we would take that assumption, and generally it gives you good results for many applications. Okay, we would see that. Sorry. No, I think you still could not understand my point. Just look at that. See, this is, let's say, a rod. For example, you put this rod one side at temperature T1 and the other side at temperature T2. You understand that? And what I do is I put few sensors along this rod. I am just talking about one-dimensional heat transfer. I say that this is one sensor, this is second sensor, third, fourth and fifth and sixth sensors are being placed on its ends, right? Now this is sensor 2, 3, 4, 5 and 6. Let's say this, let me represent it as T6. Now the point is, this T1 is a value of, let's say, 20 degrees centigrade, and this T6 is a value of, let's say, 5 degrees centigrade. Now I say that there is no change with respect to time. It means 20 remains 20 and 5 remains 5. Now this 2 may be like at a temperature of 18. This 3 may be at a temperature of 15. This may be at 11, let's say. This may be at 9. And this may be at 7. This may be at, let's say, 8. And this may be at 5. Right? Now the point is, would there be any heat transfer from this end to this end? It should be. But my point is that at every point within the medium, your temperature is not going to vary with respect to time. And why? Because there is the difference. Remember one thing, heat transfer is a non-equilibrium phenomena. Non-equilibrium. Now why do you call it a remember this point, very, very important, that heat transfer is a non-equilibrium phenomena. You do not find any kind of heat transfer in the equilibrium. Why? Because if it comes to equilibrium, it means all those temperatures, they become equal to each other and there is no heat transfer at all. Okay, why? Because if all the forces, they become equal to each other, or let's say their summation becomes 0, what do you say? Would the body still move or would it be static? It would be static. It means there is no change. So that is the equilibrium phenomena. So in static structures, you want your body to be at static equilibrium. Okay, but in thermal systems, if you want to transfer heat from one side to the other, so that is what? A non-equilibrium phenomena. Remember that. And why it is a non-equilibrium phenomena? Because you consider these things. Those temperatures are not going to be equal. If those temperature becomes equal to each other, obviously the heat would stop being transferred. Okay. So this is my point. I hope you understand it. Now temperature does not vary and the heat transfer rate remains constant. This is what you call it a steady state. That is why, if you remember, I wrote this quantity, just a very unconventional thing, that this thing would be what? That this heat transfer rate with respect to time would be 0 for steady state. Right? You understand that? So I hope I have been able to tell you the whole objective of the steady state term and the non-equilibrium thing. Okay. Now, this temperature or heat flux remains unchanged with time. You see, the temperature or heat flux remains unchanged. Heat flux does not become equal to 0. When it becomes equal to 0, it means temperatures are equal. Okay. So with time during steady state heat transfer through a medium at any location, although both quantities may vary from one location to another. Remember this. Although these quantities may vary from one location to the other. If you look at the heat transfer rate between those two, temperature difference is what? 15 minus 11, 4. What is the temperature difference between these two? Let's say if this is 8 minus 5, this would be what? 3. So within those locations it can change, but it would remain constant. If the temperature difference remains the same, heat transfer rate would remain the same, but it would not change with respect to time. This is what steady state is, right? So this is a bit confusing. Please try to understand this thing. Now see, just look at these two examples. At time equals 2 p.m. and at time equals 5 p.m. This is the variation of, let's say this is the heat transfer for one wall and this is the heat transfer for the same wall at a different time. You see, this side is at 15 degrees centigrade and this side is at 7 degrees centigrade. And even after 3 hours, it would remain the same. This is what steady state is. Okay, and similarly, if this temperature is, let's say, at a temperature of, I'm sorry for that, this may be at 15 degrees centigrade and this may be at 7 degrees centigrade. So after some time, it would be different. And obviously, this Q2 dot would not be equal to Q1 dot. But in this case, it would be. Okay? For a very short time. For a very short time. Okay. So During transient heat transfer, the temperature normally varies with time as well as position. You remember I told you this temperature is what? This is a function of x, y, z and t. If you remember, velocity was a function of x, y, z and t. Okay, for 1D systems, these two dependencies would be finished. They would not be there. For 2D, only one would vanish. For steady state, this temporal term would vanish. Okay, you know these dependencies. In the special case of variation with time but not with position, just look at this definition very clearly and just keep this thing into your mind. We would discuss those things once we go for the transient heat transfer, right, later at some later stage. I would not explain this term, but I would read this statement. In the special case of variation with time but not with position, it means temperature is just a function of T, right? The temperature of the medium changes uniformly with time. Obviously, uniformly at every location the temperature variation would be if at this point temperature is being varied by 1 degree, at all the other locations it would be varying by 1 degree. So such heat transfer systems are called heat lumped systems. Okay, variation with respect to time only, not with respect to space. So that these are the systems which are considered lump systems. Okay, we will talk about that later on. Right, now this is about the multi-dimensional system. If you look at this cube, it is a 3-dimensional system. If I ask you that I have insulated this side, let's say this side and this side. Now only two sides are left uninsulated, this one and this one. So where would that heat would go? That heat should travel in this direction only, isn't it? So if you make the sides insulated, it means the heat is not allowed to go towards that side, right? Now this is how it goes. But for multi-dimensional heat transfer, we would talk about the temperature distribution in the 3D systems, right? I would generally derive the most general form of the heat conduction, not the conduction equation, by the way, it is heat diffusion equation. Okay, and then we can just skip few terms, we can nullify a few terms to find out 1D heat transfer, steady state heat transfer or 2D heat transfer kind of phenomena. Okay, just look at that. If you say that this is the wall, for example, this is one wall, and I say that those few points are having same temperature, and I join these points, I just join them. So this curve would be known as an isotherm. Isotherm means the surface or the curve which is joining those points having the same temperature. You understand that, right? So this is something which is known as isotherm, right? So let me go for a very generalized definition of Fourier equation first, Fourier law for heat conduction. What was the Fourier law? That was Q dot equals minus Ka . Now if I write it down in a very general form, that would be written as minus Ka and this is for 1D only, because why? Temperature is showing dependence on x only. Now for the very general form, I would write this Q dot equals minus Ka this delta is kind of vector quantity. Now you remember this sign? What is that? Partial by partial xi, partial by partial yj, partial by partial z, You remember that inverted delta? What is that quantity? Del, right? So this is del T, gradient of the temperature field. So this is partial by partial xi plus partial by partial yj plus partial by partial zk. Now see, I would just write down, okay, let me write down this equation over there. I would say that this q dot would be a vector quantity, isn't it? And you can write it as minus Ka partial T by partial xi plus partial T by partial yj plus partial T by partial zk. And remember, I am assuming that this is what? A kind of a homogeneous surface as far as the thermal conductivity is concerned. I am not considering variation of K with respect to spatial variables. And you know that if any property is changing with respect to space, the dimensions, that is something which is known as what? In your materials course, you might have seen those terms, homogeneous and heterogeneous, right? So this is heterogeneous dependence is not there. I am just assuming this is a homogeneous kind of material as far as the property K is concerned. In every direction, K remains the same, right? So remember this thing, this q dot is what? This is a vector quantity, right? Now, for example, just look at that isotherm. Always heat transfer is normal to that isotherm. Heat transfer is normal to that isotherm. Why? Just let me give you one example. Just look at this wall. I assume that wall to be of an infinite height. This surface, this complete surface is at T1, this complete surface is at T2. Can I call these two surfaces as two isotherms? If those two surfaces are having the same temperature at all the points, can I call those two surfaces or those two sides as isotherms? Right? Now, if this is a 1D heat transfer, the heat would go from this side to this side normal to these isotherms. Right? So it means that heat transfer would be normal to the isotherm. If you see any isotherm and you want to see where the heat is going, so that direction would be normal to the isotherm, right? So for example, in calculus, if you are given any kind of surface, you can find out its tangent and you can then find out its normal from your calculus course. If any surface equation is given to you, you can do these kind of things. Okay, so this is how they are related. So in general, if I want to represent q dot, I would write this minus Ka partial T by partial n. This n shows the normal direction, right? This n shows the normal direction. But anyways, this is the most general form of the heat transfer conduction equation. This is the Fourier law, right? Now this is again some example of the multidimensional heat transfer. I would come back to this point. Now let's derive this heat diffusion equation. I hope you can see this cube very clearly at the back. Can you see that cube? So if you look at that, this cube is a small volume inside a big system. We have isolated that cube, just make it bigger, or you can say just zoom in, and this is my coordinate system. I would say this is Z, this is X, and this is Y. Okay. Now, for example, if this surface is basically, you can say X axis is normal to this surface. So I would represent the heat transfer which is going in. This is Qx. Now see, that small cube is a part of a bigger system. So it means the only heat transfer possible from the bigger system to that small cube is through conduction. Isn't it? We are not talking about any kind of radiation now. We are not talking about any kind of convection now. Right? It is just about conduction. So if it is conduction, it should be a part of a larger solid, or let's say a liquid volume, or even a gaseous volume, even if the gas is not basically a very good example in this case, but you can consider a volume of water or liquid, or let's say a solid. Okay. So what you can see is you have this cube, and on this side I say that Qx is the heat transfer which is going in, and obviously there would be some Q which is going out of this side. There would be some Q which may be coming into this system along this Z direction, and there can be some Q which is going outside this cube, and similar is for these lateral sides. Now for example, at this side I say that this is Qx. Now remember, if I write down Qx, just think it is Qx dot. Okay, because we are talking about heat transfer rates. We are not interested in the amount of heat transfer. This is heat transfer rate. So just consider it as I am talking about the heat transfer. I would not put the dot every time. So this is Qx, and then on this side, because now the heat, that heat or that particular amount of heat has traversed certain distance in the x direction. So can I write this Qx plus dx? Now dx is this thing, you can see it. Dx is this dimension. Can I write this thing as Qx plus dx plus dqx? A very small change would be there. A very small in the heat transfer rate would be there, obviously, because heat has traversed some distance. Now I am just talking about the very generic form. So it may change. I am not talking about steady state. It may change because I am talking about the generic form. So I should write it in this form. Chain rule. No, not the chain rule. What is that, by the way, where you subtract and where you multiply it? It just skipped out of my mind. Sorry? No, come on, don't say it. So anyways, just check it. So by the way, you can write this thing because there is no change if you multiply it with dx and divide it also dx. By the way, it is not multiplication and division. It is something which is chain rule of differentiation. So you can check that. So I would say this Qx plus dx would be equal to Qx plus dqx over dx. So you can say that in the x direction, on the left side, this is the amount of heat which is entering the system, and on the right side, this total is the amount of heat which is going out of the system. Now similar is the case. Okay, let me write it down, everything very clearly over there from the very beginning. I would say Qx dot, there are Qy dot, which are entering the systems from the positive side, from the positive coordinate sides, and then you would have Q dot x plus dx would be equal to Q dot x plus dq dot x over partial x dx. So this is energy stored and this is energy out. I'm sorry for that. Thank you for that indication. So that's why I asked you to, I'm sorry. So, but anyways, you can have those slides. So E dot in plus E dot G, and then you would have energy stored and energy out. Now these three terms, they were the energy in quantities, isn't it? On that cube, you can see that. If you see all of those three terms, Qx dot, Qy dot and Qz dot, they are energy in terms. And x plus dx, y plus dy and z plus dz, they are what? Outgoing energy terms. So I can say these are the energy in terms and all of these are energy out terms. I'm sorry, let me write it over there. These are energy out terms, right? So what you need to do is, these energy interactions are due to what? These energy interactions are due to conduction, isn't it? So you can write this qx dot as minus k a partial t by partial x, isn't it? You can write this thing as minus k a partial t by partial y. You can write this thing as minus k a partial t by partial z. Now what is the area which is being used to transfer energy from this side? This area. Now what is this area? This is dy multiplied by dz, isn't it? Dy multiplied by dz for qx dot. So I would write this area as dy dz. Similarly this area would be dx dz, and similarly this area would be dx dy. You understand that? Okay. Now see, there is one interesting thing. If you see this E out minus E dot in equals Eg minus E stored, that's how I can write it, isn't it? Now if you look at it, E out minus E in, because these are what? These are vector quantities, isn't it? So I should subtract x from x, y from y, and z from z. So now look at that. If I subtract this quantity from this one, this qx dot would be cancelled by this one, isn't it? Qx plus dx minus qx. This is how I can define this side of the equation for x direction. Qx plus dx minus qx. Similarly qy plus dy minus qy. Similarly qz plus dz minus qz. So in the end I would come up with partial qx over partial x dx, right? And then I can have partial qy over partial y dy, and then I would have partial qz over partial z equals this right hand side. You understand that, isn't it? So in the next class slide, let me quantify this term partial. By the way, this is partial q dot x over partial x dx. How can I write this thing? This is partial by partial x. What is q dot x? Minus ka dy dz partial t by partial x dx, isn't it? By Fourier law of heat conduction. So if I say that this k has no dependence on x, that's what I was talking about, that homogeneous material. This k has no dependence on x, so I can simply write it down out of this scalar, and I can represent it like partial square t by partial x squared dx dy dz. Now similarly I can write down the final form of those equations as minus k partial square t by partial y square dx dy dz. You can find that out yourself, no problem at all. It is quite straightforward. Don't forget to put a dot over there. Minus k partial square t by partial z square dx dy dz, right? And finally if I write down all of those things, I'm sorry for that. just look at this quantity. I would quickly write it down, so please bear with me. We have just 1 or 2 minutes left, so I need to complete it in time. So partial square t by partial x square, so I would take k as the common from all of these quantities, and obviously I can take dx dy z as the common from these quantities. So I would just write it down as if in the most general form, and then I would have plus partial square t by partial y square plus partial square t by partial z square dx dy dz, right? And what was there? Energy stored term and energy generation term, right? So energy stored minus energy generation, energy generation minus energy stored, so this could be plus and this could be minus. Now see, this energy generation equation, because I know it is what? It is a volumetric process. So can I write this as energy generation per unit volume multiplied by total volume? This is energy generation per unit volume. So if I multiply it with the total volume, can I write it like the energy generation per unit in the complete volume? I can write it like this. Sorry? No, this was not flux. This was not flux. This is this Q dot G. Generally, because you represent this generation term as energy generation, the strength of the heat source, just like a heater, the strength of the heat source is given as energy generation per unit volume. So if I have this energy generation per unit volume, I need to multiply it with the total volume, isn't it? That's how I can get it. Now my point is, this energy stored per unit volume can be represented as rho Cp partial T by partial T. This is how you define energy stored in any material. Rho Cp, you know what is rho, this is the density. Cp is specific heat, partial T by partial T. Why? Because storage is something which is a temporal phenomena. You say that storage is increased with respect to time. That's what it is. Now storage cannot be kind of a steady state thing. Why? Because if something is being stored, obviously it would take time. If time is not there, storage is not there. Okay. So this rho Cp partial T by partial T, this represents energy stored per unit volume, and I can multiply it with the total volume so that I can get the final quantity. So finally I would get this quantity as minus K partial square T by partial x square plus partial square T by partial y square plus partial square T by partial z square, and then I would have rho Cp partial T by partial T minus Q dot G. I'm sorry, this is minus and this is plus. And if I just change this negative sign, so I can write it as partial square T by partial x square, obviously K would be there, partial square T by partial y square plus partial square T by partial z square minus Q dot G equals rho Cp partial T by partial T, right? And I can write it down, if I just bring K over there in this denominator, rho Cp over K. Do you remember this term? What was that? 1 over alpha, isn't it? So I can write it down as 1 over alpha partial T by partial T. So this is partial square T by partial x square plus partial square T by partial y square plus partial square T by partial z square. I'm sorry, this is minus Q dot G. Minus or plus? This would be minus over there, so it would be plus over there. Thank you. Now obviously this rho Cp by K equals 1 over alpha. Okay, you are talking about this thing. Thank you so much. I need to rush now, right? So you can see I am feeling the pressure. So that's what it is. I mean, this is what is known as heat diffusion equation. This is something which is known as heat diffusion equation. Now, for example, if I ask you to look at the steady state term, look at the steady state equation. So this left hand side would be equal to 0. If there is no source, just like a heater or let's say any generator, this term would be 0. If I ask you to look at steady state one-dimensional heat transfer, you would have this equation. You understand that? If you look at 2D steady state heat equation, so you would have this equation. You might have seen this term, this equation. You remember that? So this is Laplace heat equation, Laplacian form of that heat equation, right? So this is heat diffusion equation. We will talk about its applicability in the next lecture. Thank you.